So, without further ado, I'll introduce Professor Frank Mitloehner, and I can't pronounce his surname very well. Sorry, Frank. Frank's an air quality specialist at the Cooperative Extension at UC Davis. He shares knowledge and research domestically and abroad with students, scientists, farmers and ranchers and policymakers and the public at large. Frank's also the director of the Clear Centre, which has two main aims, which is research and communications. The Clear Centre brings clarity to the intersection of animal agriculture and the environment, which helps our global community understand the environmental and human health impacts of livestock so we can make informed decisions about the foods we eat while reducing environmental impacts. I won't say any more. Feel free to introduce yourself, Frank, and the purpose of your visit to Australia as well. And thanks very much for giving us the webinar today. Over to you, Frank.
Thank you very much, Matt. I appreciate the invitation and really happy to be here at the University of Tasmania. What a beautiful spot in the world you have here. I've never been to Tasmania. I've been to Queensland several times before, but this is really very special to us. Yeah, so I do work at the University of California in Davis, and I've been there for the last 20 years. I teach and do research and also extension, so I have a three-way split appointment. And much like many of you, I spent my daytime getting grants, publishing papers, doing all the good stuff, teaching undergraduate and graduate students. Have a lab with about 20 people at the Clear Center. And also I'm an extension specialist, and that means that I take information from the university and share it with the rest of the world that wants to know. So my main work is on characterizing criteria pollutants and greenhouse gases from animal agriculture and mitigating those pollutants. And today I want to talk to you in particular about methane, because that's obviously a very hot topic. And I think we all understand it's not just about methane and it's not just about carbon, but we also have to deal with other issues. And that's not just, you have a question, Matt?
Yeah, I do, sorry, Frank. I was just going to say, for people, for other than you and I, there's three dots up in the corner of the screen. If you want to blow up Frank's picture, the three dots in the corner of his video, you can go pin this video and his video will fill the screen basically, as opposed to seeing all the other participants. That's just for everyone else. Thanks, Frank.
Yep. Yeah, so while we all understand that methane is not the only pollutant in the world, there are others. It's also not just about pollutants. I mean, sustainability includes multiple issues, spanning from environmental sustainability that includes air, water, and climate, to animal welfare, to worker issues, attracting and retaining a qualified workforce, food safety and financial viability. All of them are important sustainability considerations, many of which we are dealing with at the Clear Center that I'm directing. So I will now share my screen and talk to you specifically about methane, because that is a topic that everybody knows is hot and oftentimes misunderstood. I share with audiences in California, throughout the United States and internationally, the journey that we have undertaken in and around methane. And some of that I want to share with you here today. So everybody here knows that the matrix that's largely being used throughout the world is GWP100, that characterizes methane and nitrous oxide as being 28 and 265 times more potent, so to say, than CO2. And all emissions are converted to CO2e equivalent, carbon equivalent emissions. So pretty much methane is currently depicted as if it were a CO2 on steroids. But everybody also knows that methane is a short-lived climate pollutant, and it actually behaves differently in the atmosphere and how it warms. And I just want to highlight a couple of slides that I think are really important because it makes methane so different from other pollutants. This slide here, global methane budget, might not be new to anybody here, but it is new to many people I talk to, namely stating that methane has actually a budget. It's not just produced like many other greenhouse gases, but it's both produced and destroyed. Not just are there sources such as fossil fuel production, use, agriculture, biomass burning, and so on, amounting to close to 560 teragrams, but there are also sinks, and they are amounting to close to 550 teragrams. And one of the greatest sinks, of course, is the process of hydroxyl oxidation, where hydroxyl radicals, destroy methane in a relatively short time period. And that leaves the difference between the sources and sinks still a number we seek to reduce, but certainly one that's different from just looking at sources. And so this whole dynamics of methane, not just being produced, but also destroyed, affects its behavior on warming. You're also aware that methane is a short-lived climate pollutant with a half-life of a little over a decade versus those of carbon dioxide and nitrous oxide, which are long-lived climate pollutants. Not bore you with that because I know that everybody here on the call knows these things, but I think it's worth mentioning that CO2 and methane are really quite different in how they accumulate or not. And while CO2 is a stock gas that accumulates every time we burn oil, coal, and gas, we have methane that is not a stock gas, but a flow gas, because it's not just produced, but also destroyed. And if we have a constant source of methane, then we almost have an equal amount of what's being produced by that constant source also being destroyed. And some people view this as, oh, methane is not a problem. That is, of course, not what it means at all. If we increase methane over time, then we increase warming, and we certainly don't want to do that. But if we have a constant source of this gas, near constant, I should say, in fact, if we reduce methane by 0.3% annually, then we have a constant source of methane causing constant warming. But what is most important to me is what happens when we reduce methane. You will also see here on several of these slides that I'm about to show that they stem from Miles Allen and his team from the University of Oxford. And one of these co-authors here is David Frame from New Zealand. I will visit with him next week. They, for quite some time now, had invested significant efforts into separating the narrative around CO2 and methane, and I think for very good reason, because oftentimes this is all just confused as being pretty much the same, with one gas being more potent than the others. You might be familiar with the new matrix GWP star. GWP star was really born out of necessity that that this old matrix GWP100 seems to overestimate constant sources, such as a constant cattle herd over 30, 40, 50, 60 years by a considerable factor of 3 to 4. And this criticism has been raised by Miles Allen's team. It has been raised by my team for a long time. And they developed, these Oxford colleagues, this new matrix GWP star, which is also based on GWP100, but throughout different time points in 20-year increments, along with a correction factor. And GWP star actually takes into consideration the short lifespan of this gas, including the atmospheric removal through hydroxyl oxidation. And why this is so important and how it's so different from GWP100, I will show you in a couple of slides. Before I do that, I want to just mention that this first bullet point here, namely the notion that GWP100 drastically overstates the impact of constant sources, that has now been reported at the IPCC, Intergovernmental Panel for Climate Change, AR6 report from 2021, where it says in chapter 7 on page 123, and I quote, expressing methane emissions as CO2 equivalent emissions using GWP100 overstates the effect of constant methane emissions on global surface temperatures by a factor of 3 to 4. And one might think, wow, this is a matrix that has been used for the last 30 years. How can that have happened, that it overblows the impact of this gas on warming by so much, as long as you have constant sources? People have kind of woken up to the fact, and see in the chapter 7 the mentioning of GWP star throughout, and it might actually be one of those developments where an old matrix might, for certain applications, I want to repeat that, be replaced with something like GWP star that looks more at a rate of change of methane over time and its actual impact on warming, and not just its carbon equivalence. I want to show here on this slide, also from Miles Allen and colleagues, 3 scenarios. The first one is one where methane over a period of 30 years increases pretty strongly, so by 35%. The second one where over 30 years, methane slightly decreases by 0.3% per year. And a third one where methane is strongly decreased by 35%. How would these scenarios, the increase, the stable, and the decreasing amount of methane, be depicted using GWP100, the old unit from, or matrix from 1990? In all 3 cases, a significant amount of additional CO2 equivalent emissions would be produced. We know that at least in the second and third scenario, that is wrong, because this gas, methane, is not a stock gas, it's a flow gas. And if we reduce it, then it's impossible, from a physics perspective, impossible that we have increasing CO2 equivalent emissions leading to increasing warming. We contrast this with GWP star. We find that only in the top scenario, where we increase methane by a lot, we see additional warming equivalent units. That means additional warming added to the atmosphere. We do not want to increase methane over time. We all know this will have a very significant impact on warming that must be avoided. But if we hold stable or slightly reduce methane, then we don't see blue north of the x-axis, meaning no additional warming. But because on this in this scenario here, there's a slight reduction of 10%, we now see a negative sign in front of the number. And the blue is now south of the x-axis, meaning there's some negative warming occurring here. And when we reduce methane by a lot, let's say 35%, then we see a lot of negative warming, much as what we achieve when we plant forests, which of course also take carbon from the atmosphere. So in other words, if we hold methane stable, we don't cause additional warming. If we reduce methane, then we can reduce warming. And this strong reduction of methane reduces warming, offsetting other greenhouse gases, let's say nitrous oxide and CO2 from the same sector, let's say the dairy sector or the beef sector of a given locality. So a reduction of methane makes a lot of sense. It's very important. And if that reduction is strong enough, we can achieve a point of climate neutrality, a point whereby an industry will not cause additional warming to our planet, and therefore abide by the Paris Climate Accord, which is temperature oriented with respect to its goals. In my opinion, we should be having the same goal of not causing additional warming. And in order to achieve that, we need a matrix that is fit for purpose to characterize that. So the question now is, can this be achieved? A strong reduction of methane by the order of 35%. Can this effect here be achieved? Before I answer that question, I want to show you 3 more scenarios, one for rising, one for constant, and one for falling emissions. And I will describe 2 different sources. The first one is, let's say, a power plant, which over 30 years ramps up production of power, and as a result, ramps up emissions of CO2. The second source could be a feedlot, let's say, with 10,000 cattle at first. Over time, over 30 years, it grows to 15,000 cattle. As a result, the methane will increase linearly. How would this linear increase of CO2 and the linear increase of methane impact warming? Well, the linear increase of CO2 would lead not to a linear increase of warming, but to an exponential increase due to the fact that it's a cumulative stock gas. But a linear increase of methane would cause a linear increase of warming. Nothing new here. What's more interesting is what happens with constant emissions. Let's say our power plant over 30 years were to produce the same, a constant power load, then that would lead to constant CO2 emissions. And with respect to warming, the constant CO2 emissions would lead to increasing warming, again, due to the cumulative nature of this gas. But let's say if our feedlot with 10,000 cattle were to be 10,000 cattle over decades, then that constant methane emissions would lead to constant warming and no additional warming. Constant warming, no additional warming. So that would be in agreement with the Paris Climate Accord of not causing additional warming. But most important here for me, what were to happen if we reduce both CO2 and methane? Let's say our power plant here were to be ramped down over time and then eventually be shut down, and that's net zero carbon or carbon neutrality. So in order to achieve carbon neutrality, the power plant would have to be shut down at some point. How would this reduced CO2 over time affect warming? Well, it would increase the warming all the way to the point when we shut down the power plant. And only at that point, we would have a plateauing of the related warming. That's what it takes to cause no additional warming from fossil fuel sources. We have to stop burning them to achieve a plateauing of the warming. Whereas if we reduce methane, we have a pretty instantaneous impact on warming. So to me, this graph, like no other, shows that methane is not just a more potent greenhouse gas than CO2, but that it behaves very differently in the atmosphere. And that's true for rising, for constant, and falling emission scenarios. To just use a matrix saying it's 28 times more potent than CO2 does not describe what's really happening to warming. And because warming is what it's all about, that's why we care about this gas, we should use, in my opinion, a matrix that's fit for purpose. And that does not mean we should get rid of GWP100, but in my opinion, it means in addition to GWP100 that the world has become so accustomed to, we should also use GWP star in order to describe the actual impact of a source on warming. So now back to my question, can we achieve a strong reduction of this gas, methane, leading to negative warming? In California, where I live, we have pretty strong environmental laws. Actually, the strongest ones, the strictest ones in the United States. The most recent one is called SB 1383, and it mandates a 40% reduction, 40, a 40% reduction of methane to be achieved by the year 2030, so in 7 years from now. Might sound familiar to you because you have 2030 goals. Ours is not so much a greenhouse gas goal in general, but a methane goal in particular. And what's special about the California one is that we are not using rules, regulations, fines, and taxes to achieve the 40% reduction. I would call that a cane approach. But instead, we are using an incentive approach, a so-called carrot approach of financially incentivizing methane reductions from all sectors, and that includes agriculture. So instead of penalizing agriculture, the state of California decided to incentivize reductions of emissions and achieving the emission goals that way. The goal is to reduce 7 million metric tons of the dairy sector by the year 2030. And here's how that's going. So the 40% reduction by 2030 is the law. So how is that being addressed? First of all, we do have a slight attrition number. So our dairy herd number is slightly going down by about half of 1%, so 0.5% annually. And it has been for a while. That, along with milk production improvements, will lead to 2.6 to 3.3 million metric tons of reduction annually. Then we have so-called alternative manure management practices. These are solid separators and other means of keeping volatile solids out of the lagoon where the manure is stored, leading to relatively minor reductions. And the range is listed here. Much more important are the so-called anaerobic digesters. I will talk about this in a minute. These are covered lagoons that trap biogas and convert it into something else. I'll talk about this in a second, leading to 4 million metric tons of reductions. And feed additives that are not in use yet, but will be in the future, that have a range of reduction potential from 250,000 to 2 million metric tons of CO2e. So cumulatively, if you add all of these together, these different reductions will amount to something exceeding the 7 million metric tons. So we are very bullish in predicting that the 40% methane reduction will be achieved by the year 2030. And it will be achieved through a voluntary incentive-based approach. For example, the state of California currently financially helps farmers to put covers over their manure storage. You see here what's called a covered lagoon. It's a type of anaerobic digester, and it's bulging out the plastic. The gas underneath is biogas, 60% of which is methane. The biogas is then purified and made into a transportation fuel called renewable natural gas. And this transportation fuel is then used to power heavy-duty trucks and buses. This technology alone, these covered lagoons, has already, over the last few years alone, reduced 2.2 million metric tons. And that means the dairy industry has already reduced 30%, has already achieved 30% of its methane reduction goal. So we've come a long way, considering we only started a few years back. And we are doing this, we are reducing this methane without breaking the bank, because when you convert biogas from a dairy into transportation fuels, you get carbon credits. They're called low carbon fuel standard credits. Assuming that an average cow in California produces $4,000 per year in milk sales, these biogas to transportation fuel credits amount to 2,000. So roughly half the amount that a dairy gets, excuse me, that a dairy gets through the sales of their milk can now be achieved through the sales of carbon credits. The state considers this a double whammy because we are reducing emissions from the dairy industry using this technology, as well as emissions from the transportation sector, which no longer burns the much dirtier diesel, but the much cleaner renewable natural gas. And this is what a fuel station looks like that receives dairy renewable natural gas and that puts that into those heavy-duty trucks. In addition to the biogas production and transformation into transportation fuels, we're doing a lot of research at UC Davis, where I work, around feed additives, around genetic selection, around vaccines, around boluses, and so on. Here you see some results from various feed additives that we are working with. And while this year only shows methane reductions, we are of course also looking at other co-benefits and or unintended consequences, which are oftentimes forgotten and shouldn't be. For example, a co-benefit could be that no other pollutants are generated, or even some of them might be reduced, like nitrogen emissions. An unintended consequence of using an additive could be impacts on animal welfare, or residual toxins in milk or meat, or price, availability, impacts on palatability. Some of these additives are not really all that attractive to animals, and they will reduce feed intake. All of these things have to be looked at, and not just methane, in my opinion. We have recently conducted several studies looking at how our California dairy industry, which is the most productive one in the state, in the United States, how that dairy industry can reach climate neutrality, or a point of not causing additional warming. On this slide, you see the years 2020 to 2030. We use GWP star to characterize the CO2 warming equivalents. You see in gray here what happens with business as usual. If we don't reduce methane, but we just wait for herd size attrition to do its job, then we will never achieve climate neutrality, meaning the point by which we cross the x-axis. If we reduce methane from manure storages by 40%, that's what the law calls for right now, that's the light blue, then we will reach climate neutrality for the California dairy industry by the year 2027. And if in addition to the manure storage methane emissions, we also use a feed additive that reduces, let's say, 10 or a little bit over 10% enteric emissions, then we also achieve climate neutrality by 2027, and but to a larger extent than through using manure emissions alone. So we are taking our industry onto a journey to a point by which they no longer cause additional warming. And I think that's really what we should strive for. We are not promoting carbon neutrality, because carbon neutrality goes much further, and we are hesitant to use this term because we don't really think that we can achieve a reduction of almost a total reduction of greenhouse gases, either by direct emissions reductions or purchases of offsets. And we don't think that it's really needed for the livestock sector to reach carbon neutrality. What we need to do is we need to reduce methane by enough to offset the overall facility emissions. And that can be done when you reduce methane by something like 20, 30%. If you're interested in how we at the University of California in Davis have met the call of advising our state, the state of California, on getting onto a pathway of reducing methane and achieving climate neutrality, and I encourage you to use this QR code, and you'll get to a white paper that I wrote together with my colleagues Ms. Cabrera and Dan Sumner. If you are interested to seeing how GWP 100 versus GWP star perform modeled for California dairies, then there's this paper here. It shows a really nice alignment of global warming potential star with climate models, and it shows how the differences in behavior and warming behavior is really well expressed using this GWP star. I want to make it very clear that GWP star will not replace GWP for all purposes, but for certain purposes, such as rate changes over time, I think it's a very fine means of characterizing those changes. So that is pretty much the gist of my presentation. If you are interested in looking at some of the Excel spreadsheets that are underlying some of the modeling pathway to climate neutrality for US beef and dairy, is depicted on this left white paper, which also contains some of those spreadsheets that are free of use. On the right side here, we have produced a short YouTube video, 5 minutes, that helps farmers and others, policymakers, journalists, and so on, to understand methane and how methane is different and why it's important for us to understand it, why it's important for us to quantify it correctly, and why it's important for us to mitigate it. This is a little 5-minute video free for you to use, and of course share with whoever's interested. I'm on Twitter, GHGGuru is my handle, and the CLIA Center that I'm directing has a webpage, clear.ucdavis.edu is the address. So with that, thank you very much for your attention, and I'm happy to entertain any questions that you might have.
Thank you very much, Frank. That was a very stimulating and captivating presentation. And I should say thanks to everyone who joined, particularly the Hobart people I can see on the line, given it's a holiday. So happy to take any questions if anyone wants to raise their hand. While those hands are busy being raised, Rowan is clapping and has got a hand up. Rowan, do you have a question?
Yes, hello. So you know that Matt's running the carbon storage partnership for the livestock industry for Australia. Is it possible to influence the rate at which methane is broken down or absorbed? And should we be looking at that as well as carbon sinks?
You mean how methane is the soil sink of methane or the atmospheric sink of methane?
Well, are there any ways in which we can influence that so that that side of the equation happens quicker?
Yeah, so what contributes to the atmospheric removal, which by far is the most important one, are hydroxyl radicals. And these hydroxyl radicals are the atmosphere, and we can't really modify those concentrations significantly or at all. Yeah, any kind of oxidation of methane will lead to its conversion to CO2. So of course CO2 is where the methane from livestock, where the carbon for the methane from livestock, where it comes from, because the plants that our animals eat, while they were alive, they took on CO2 during photosynthesis. That carbon becomes cellulose, is then, when it's ingested by animals, converted into methane, and after approximately a decade, that's converted back into CO2 during this biogenic carbon cycle. Can we modify that? Can we modify this process? I don't think that we can accelerate the atmospheric removal of methane. But by reducing methane, of course, we are replenishing less than is naturally destroyed. And so that makes that gas go down. And that means the warming goes down.
How does that sound, Ron?
Okay.
I think just, and I sort of had an adjacent question to that, Frank. What you're saying is after 12 years, one methane molecule then goes back to CO2 and hydroxyl. And so then that CO2 enters the other pool of CO2, which is a stock gas. And so that contributes warming over 1,000 years sort of thing. But the CO2 that first come from that methane probably come out of the atmosphere the year before into grass. The cow eats the grass, produces methane. The methane lasts for 12 years, degrades into CO2.
Yep.
And that CO2 goes back into the atmosphere and potentially back into grass.
Yeah. So the CO2 that results when methane oxidizes is not new and additional CO2 added to the atmosphere, because that CO2 was CO2 before it went into the plants during photosynthesis. So if you do the mass balance or so, there's less CO2 coming out of this whole process than went into it. But of course, while that methane is in the atmosphere during those 12 or so years, that gas has a significant radiant forcing. And so during that time, it warms the planet, and that's the piece that we want to reduce. But in this biogenic carbon cycle in general, we are not adding additional carbon, we are recycling carbon over and over. But that's not to say that methane doesn't matter. It just means that in contrast to fossil fuels, let's say, that are always additional carbon, because we're taking carbon from the ground and we are burning it and adding that carbon into the atmosphere. Same is not true for the livestock end. By the way, this whole issue of how we quantify and how we mitigate methane, biogenic methane, is one that I brought to the forefront with the United Nations FAO, the Food and Agriculture Organization of the United Nations. And the whole issue of what matrix to use and how to mitigate and so on was debated by 65 members of a global task force, many of whom are IPCC members. And this global task force is about to release a final report that will come out in April of this year. And so you will see that report. It will discuss all those issues that I just scratched the surfaces for, including GWP star and when to use it, when not to use it, different approaches of mitigating methane, accounting for it, and so on.
Thanks very much, Frank. Ian Hunt's been patiently waiting with his hand up. If you're there, Ian.
Hi, thanks for your presentation.
Feel free to turn your video on if you want, Ian.
Hello. Hi.
That looks better.
Okay. Look a bit like a rabbit. I'm an unashamed fan of a certain governor that used to rule California, and he, at some point, only for various reasons, but he waxes lyrical about the unintended consequences of his awakening to environmental concerns. And so one of the things he says, I gain from these changes when he converts his Hummer from diesel to electric, it's got more horsepower. So I was wondering where your unintended consequences are coming down for the sorts of things you're doing this decade. Is it positive? And obviously there's some positive, some negatives. What have you found? Is there going to be
So a negative could be that you are feeding a feed additive and all of a sudden you have a residue, a toxin in your milk or in your meat.
Yep.
That
so
will
have you
never
found
fly.
anything like that?
Yeah.
Oh, okay.
That can happen. It can also happen that feeding certain additives will lead to the taste of the feed to change and the animals to eat less. And if they eat less, and significantly so, then that will affect milk production and meat production. And that will be a no-starter, okay? If the producer knows that their animals eat a third less, they know what that will do to performance of their animals, and they will not use it. So another issue is if a additive is difficult to get hold of, it's difficult to being produced or to shipped, or can never be produced in thousands of tons that are needed, well, then it's not likely to be a winning proposition. So we need to think
What about the positive ones?
Well, there are positive ones. There are positive ones for sure. But the problem is that currently, and Matt and I just talked about this, that currently the world of scientists is super myopic around methane, as if that's the only problem in the world right now. We must reduce methane, and I agree we do, but we must not forget that the world is not just about methane. There are other things that we need to look at the same time concurrently. And this is, when I say this sounds like, oh, there's a scientist who wants to deflect off methane. No, that's not what it is. But when we make some major changes with some active ingredients that have a high potency, then we need to make sure that it doesn't affect the health, the welfare of animals, of people, that it doesn't generate other pollutants and so forth. So there are, for example, there are now means of using animal breeding to reduce methane. I have been to Scotland 2 weeks ago, and I saw that there's a genomic test to test which animals are low versus high methane producers. And you can now select for low methane cows and low methane livestock. And that will take some time to get animals replaced, herds replaced to animals that produce the normal amount of food, but produce less methane. But it will lead to 20 or 30% reduction of herd emissions without any negative impacts. So that's an example of something that's very positive. And there are others, but there are also some that are where I'm not as bullish, where I'm more cautious.
Thanks.
Thanks, Ian. A really good question. Any other questions? Paul Dean, Ian, you've still got your hand up, but I think that's a residual hand. Paul Dean has put a question in the chat, and his comment is, going back to the balloon traps over effluent, to what degree is the government offering financial assistance for this? Okay.
It took me a second to understand. Balloon traps, you mean the covered lagoons, right?
Yeah.
So these things, they work for larger operations, okay? And they are not so much of importance for you here in Australia because you have more grazing operations and so on. And I use this more as an example for how a support of the public sector for farming can help the farming sector buy into it and really make meaningful reductions. So, but back to your question. So a covered lagoon is cost effective once you have 2,000 cows or more, lactating cows or more. That's when you have enough manure in those lagoons to really pay back in a reasonable amount of time. The state in the past has partnered and paid about 50% of the capital cost, and they pay these so-called low carbon fuel standard credits and the so-called federal RIM credits. And these two credits are really what people are after, not so much the capital cost partnership, but much more the carbon credits that are on a continuing basis. And they run so high that it takes only a few years to pay something like this back. There's a real run onto these technologies. When I started in California, there were 5 or so anaerobic digesters. The state thinks that they are now 120, but in reality, they are now 240. And these are large-scale covered lagoons. And this technology alone, this one alone, will get us to achieving half of all the methane reduction in the dairy sector. Just one more statement there. Of all the sectors in the state of California that are asked to reduce methane, the dairy industry is one of them. The dairy industry has received 2% of all public funds to reduce methane. But the dairy industry alone has been by far the greatest methane reducer, achieving 30% of the publicly funded methane reductions in the state. So there's a 15 times return on investment by working with these farms to reducing methane. And our dairy sector is very bullish about reducing methane. They don't view methane as a curse word anymore. They don't view this as a liability, but they view this as an asset because they view it as methane is energy. If I lose energy, then I'm burning money and I'm doing something that's bad for the environment. So if 10% of what I feed to my cows gets lost as enteric methane, then I'm silly not to manage it. And if all that methane comes off the manure, goes into the air, and I'm not using that, then that's a silliness as well. So they view methane through different lenses now. They pretty much equate methane with energy. And losing methane is the same to them as leaving your windows and doors open in the middle of winter. That's certainly not something you want to do. But if you don't manage methane, that's what you do.
Thanks very much, Frank.
We are really working with our farms to rethink methane. Okay, and that is in no ways a greenwashing or deflecting of things or so, but this is an effort to make them understand how much they emit and what a mitigation of those emissions would do to climate and would also do to their bottom line.
Right. Thanks, Frank. Thanks, Matt.
Thanks, Paul. Deepa, you've got your hand up.
Hi, Frank. Thank you. That talk was very helpful for someone who doesn't understand animal production systems as well. Question, you mentioned that the dairy herd was reducing over time. What's driving that? Is it reduced dairy consumption, or is the problem being shifted elsewhere? Are you importing dairy into California?
Yeah, it's an important question. So what is going on is that a state like California that has a lot of regulations, not just about methane, but also many other things, is driving production out. But when we're talking about attrition, we're not talking about large attrition. We're talking about 0.5% herd size reduction per year. So let's say people who retire, sell the dairy or close the dairy, and their kids won't continue. It's that kind of thing. In some case, dairies leave California and they go to more agricultural friendly states like Texas or so. And when they leave, they take their animals with them, and with it, they take their emissions with them. And so this is a process. Many of you on the call might be familiar with that. That's referred to as leakage. So reducing herd sizes in one locality might reduce emissions in this locality. But if the demand still exists, overall, then it will be satisfied at a different location, and the emissions will merely migrate from location A to location B. Overall, the methane molecule doesn't care whether it's emitted in California or in Texas or in Tasmania. We need to reduce emissions, and we need to do that not just through herd size reductions, but through true mitigation that's permanent. And so the demand for animal source foods, for milk, for meat, is not decreasing, it's increasing. And that makes it even more important that we learn how to mitigate effectively.
Thank you. I have another question, if I may.
Yeah.
You were mentioning that they're claiming credits, right? For they're able to get finance through credits. So are these farmers also claiming any soil carbon credits from their pastures? Is there a possibility of double dipping for the same, if when you were describing the other cycle, that one's recycling versus one's actually producing? Do you see that concern or not?
Yeah, so a double dipping would be if you were to sell your credits to one entity and then you sell the same credits to another entity, and that's prohibited. That cannot be done. And currently there's no way of getting credit for anything soil related in California. In fact, the research is not even clear as to how significant any kind of soil sequestration can be at different soil types, different precipitation rates, and so on. There are very different assessments that I have seen and read. Some people think that soil carbon sequestration can be substantial and those rates could be high. And there are others who suggest the opposite, who say after a while soil carbon plateaus in its accumulation, and the potential is not as high. So I don't know how much this part of the research is settled. It's out of my area of expertise. But in general, you can receive credits through reducing, let's say, methane from your manure, and you can, in addition to that, get credits from reducing, let's say, enteric emissions that the animals produce themselves, and so forth. So that is all that you could stack.
Wonderful. Thank you so much. Thanks.
You're welcome.
Thanks, David. Really good questions. Did anyone else have any questions, comments, statements of interest? Rowan, in the chat, you mentioned in the Hebrides, sheep have always eaten seaweed. I think that was just a comment.
Yeah, so I want to just point out, seaweed is not seaweed, okay? So after I visited Scotland and Finland, I also visited Ireland recently, and they are telling me that they are feeding their seaweed to livestock. The news for them is that these temperate seaweeds are not at all the same as your seaweed, your Asparagopsis taxiformis here in Australia. You have an active ingredient in their bromoform that they don't have, and that's what does the trick. This active ingredient, by the way, is highly effective in reducing enteric methane, but when it breaks down, it also causes some other concerns, including some toxins like bromine and iodine, and they can accumulate in things like milk and meat. I've seen that myself because a colleague of mine has used taxiformis, Asparagopsis taxiformis, and 3 months after he was finished with the study, I still couldn't use the cows because their milk still contained bromine. So that might have been a result of too much with respect to concentration being fed or so. I don't know that, but to me, these issues are not settled yet, and they require more targeted research, but also research that's not too myopic into just this one gas. I see another comment there in the chat, oregano, oregano additive. So I have done a lot of research into all kinds of additives. Some of them are synthetic, like 3-NOP or Bovaer, it's called. and some of them that are considered natural. So they could be garlic extracts and oregano extracts and essential oils and tannins and so on. These compounds generally are in the family of rumen modifiers, so they change the microbial composition of the rumen content, of the microbial content, and oftentimes that's reversible. So sometimes those things are fed and they work for a while, and then after a while the microbes adjust to it and bounce back to where they were before. And the rumen microbiology is certainly capable of doing just that. The more effective means that I've seen so far are those that inhibit methanogenesis. And that is the Asparagopsis approach, that's the 3-NOP approach, where an enzymatic cascade of producing methane is disrupted, where one enzymatic step is disrupted, and that is what limits the methane production. And that seems to be very effective, also long-term effective.
Thanks, Frank. Is there any comments just following up on what Frank said there? Otherwise, I'll move to Ian. Rowan, was your comment following that one or a different question?
I can go to Ian. I think that's good.
Okay, well, just hand over to Ian.
I just have it is sort of a follow-up comment. I'm just wondering who you've seen, or whether you're doing it, conducting long-term animal welfare studies, because it might take, when you think of what happens, and one of the criticisms of a conservative approach to drug development in humans is it takes so long, to test vaccines and so on. But we want to wait for a long time. Is it possible to get funding for a 10-year program to look at a couple of life cycles and of when you're changing the microbiome of a cow permanently, and that you're doing that, what are the flow-on effects? It's a long-term project, but we're in a great rush to reduce methane in 5 years' time. There's a conflict. Are there people doing long-term studies, and is it worth trying to set one up?
It is definitely worth trying to set one up, but I don't think that this is happening currently. I'm actually quite good. I agree with you. I agree with you, not just long-term to see what happens in the rumen, but also, of course, to see what happens to the products that come from these animals, the milk, the meat. So you have to actually slaughter them and look at tissues that people eventually consume. So that's not just true for milk, it's also true for meat. In the United States, we cannot sell any feed additive at this point to reduce methane with a so-called label claim of reducing methane, because none of them have been FDA approved, Food and Drug Administration approved.
Okay, so you've already run into the...
I'm sorry?
You've already run into the sort of traditional conservative view, which has positives and negatives.
Yeah, the negative is that it hampers a speedy progress. That's the negative. But imagine we were to feed something like product A, and now everybody feeds product A because it greatly reduces methane. And then in a year or two, it comes out that there is some toxicological effect on people. Can you imagine
babies, like milk formula or something like that?
Yeah, I mean, we are talking about products that are of great importance to a population. Okay, so you do not want to have something in the milk that in any way, shape, or form has any health relevant issues associated with it. You also don't want to hamper the welfare of animals, the performance of animals. You don't want to generate other unintended consequences environmentally and so on. So I'm on the record as saying this often, and that is we have to look at these things in a holistic way and in a long-term way. It costs more money, I understand that, but it is important because we cannot and should not just be myopic on methane. And I don't want anybody to take this as saying, as Frank saying, he's not into methane. Of course, I study methane left, right, and center, but I never forget that there's a whole host of other issues that can be unintended.
Thanks, Frank. I'm just cognizant that we're nearly at an hour, and I can see that Ape made a comment there. And Frank, this will probably be your key area. Do you think that early manipulation of rumen methanogens in calves causes any shift in long-term methane emissions? So I think he means lifetime programming, early lifetime programming.
Yeah, there has actually been some very interesting research in this field where people fed calves and only calves additives, and then they stopped. And that early life feeding of these additives affected lifelong emissions of those animals. I mean, they actually changed methane as an adult as a consequence of being treated as a calf. And to me, that's a very exciting field. I haven't done research myself, but the promise of that to feeding them something when these animals are not yet functional ruminants. Think about that. Like a young calf is not a functional ruminant yet, but feeding them certain additives seems to set them up for life. And to me, this is an area that I don't understand enough about, but one that is very interesting to follow.
Yeah, very much indeed. I've just got one more comment, and then I'll just have to call it to a close. Beth had a comment there. What are your thoughts about the potential of Asparagopsis as an ozone depleter?
Yeah, bromoform has that impact. It's potent in this regard. I don't think that the concentration we are talking about is of sufficient amount to make a big dent there, but I'm pretty certain that the second that these things reach prime time, the critics will throw everything under the bathtub at them. And that includes this very issue of ozone depletion. They will definitely be very interested in potential toxicological effects. Let's not think that just because something is natural, like oregano or garlic or Asparagopsis, just because it grows naturally someplace, that in itself doesn't mean that it's harmless. We all know that there are certain mushrooms you can eat and consume, and they can send you on a several-day trip into areas that most of us don't want to go to. So just the thought that something is naturally produced doesn't mean that it's harmless. We need to look at all the intended and unintended consequences.
Well, thank you very much, Frank. I'm not sure whether people can raise a virtual applause, but I'd really like to thank you for your time. I found it very interesting, and you had a lot of good comments, and I appreciate your time. Of course, you've come out all the way from California, Davis, just to come to the Tasmanian Institute of Agriculture. Not really, but you're on part of your tour, which really appreciate your time. And thanks for all those people for joining the webinar today. What I'll do after this presentation is circulate a recording. I'll also circulate Frank's contact details, Twitter handle, and email if anyone wants to get in contact with Frank. Thanks very much, everyone, and we'll see you later.
Bye-bye. Thank you.